Select the structure of the first tetrahedral intermediate that is formed in the following reaction. So right away, it kind of implies that you might have more than one tetrahedral intermediate. And that's often the case when you have acid catalyzed processes. So let's look at what we have. We are starting with a carboxylic acid. The product is an ester. And you have an alcohol and heat. An alcohol and acid. There probably should also be heat in here, honestly, to make this work. So I'm going to add that in. But since you were given the product, it's not a trick question. You would just assume that it works and draw the mechanism. But this is the conditions for a Fischer esterification. So this is definitely acidic conditions. So you see an acid catalyst in there. So this is definitely acidic. So we want to keep that in mind, because when we have acidic conditions, that means strong bases cannot exist. Right, so that means you're not likely to push these electrons up onto the oxygen to give you a negative charge. So you want to be aware that if you've got an acid and you've got an alcohol, what you really have in this solution, right? So if you have, where do I want to write this? Maybe here. So CH3, CH2OH, and acid, what you really have is you have protonated acid around. So this would be your actual acid species. And you would have the neutral alcohol. So kind of like if you put a strong acid in water, you don't actually have a solution of strong acid in water, you have a solution of H3O plus and water. So this is the protonated alcohol, and the neutral alcohol is what you would actually have in solution. So this would be the base or the nucleophile if you happen to need those in this reaction. So with an acid catalyzed process, the first thing you end up doing is you always end up protonating that carbonyl oxygen. So we're going to grab this acid species to do that protonation. So the first thing that's going to happen is the carbonyl is going to grab a hydrogen, and you are going to break the bond between the hydrogen and the oxygen. So this is the first step, but this is not a tetrahedral intermediate. So it's not going to be tetrahedral until we make this carbon tetrahedral. And so we still have a pi bond. It's still going to be sp2 when we draw this protonated form. Okay, so this is sp2. This is not tetrahedral, that is trigonal planar. So now that we have protonated this, we've activated it towards nucleophilic addition. So even a weaker nucleophile like an alcohol could attack this carbonyl. And so after this attack occurs, then you're going to have a tetrahedral intermediate. And since it's going to be the first one that forms, that would be your first tetrahedral intermediate. So you just got to pay attention here to what happens. So our neutral nucleophile attacks, we're going to push those electrons onto the oxygen. And then we want to look at what we have formed. So you've got the phenyl ring attached still. And this central carbon, now it's got a bond to OH there on the top, another OH on the side. And you've got this new bond between the alcohol, oxygen, and the carbonyl. And then here's the important part. You didn't break either of these two bonds. So both the hydrogen and the ethyl group are still attached to that oxygen. Right? It has to attack as the neutral nucleophile. It cannot be the alkoxide because strong bases cannot exist in this acidic solution. So after this attacks, that means you have a positive charge on that oxygen. So this is your first tetrahedral intermediate. And that's what we were asked about. So we want to try to find that down here in our options. And you should see that that is option D. And so if you want to see the remainder of this sort of mechanism, there is a separate video on the Fischer esterification that contains the entire mechanism with all of its proton transfer steps.